In this module, I am going to explain group theory concept. It is very important, the point of spectroscopic techniques. In this unit, first we discuss or to explain the symmetry operations, symmetry elements, rotation, reflection through a plane of symmetry, reflection through a center of symmetry, identity operator, successive operations, point groups like C1 point group, C infinity V, D infinity H, TD OH and IH point groups, determining the point groups of a molecule or molecular ion, determinations of the point group of some molecules like trans N2F2 molecule, determinations of point group for phosphorus pentachloride, phosphoryl chloride, etc. It is very important topic, and this is the new things to you people about the group theory concept. First, I am going to explain the definitions of these or basic introductions regarding to that groups theory. For understanding the chemistry of the molecules, symmetry is very important. Symmetry is essential in discussions of molecular spectroscopy and calculations of molecular properties. For this, chemical compounds are exhibit different geometrical shapes like tetrahedral structure, octahedral structure, square planar structures. The common use of these descriptors is not always precise. Consider the boron trifluorides and BF2H, both which are planar molecules. Here the BF3 is correctly described as being trigonal planar. The bond angle is 120. The bond length distance is 131 picometer. It is correct to say that boron center in BF2H is a pseudo trigonal planar environment. But the molecular symmetry properties are not the same as those of BF3 molecules. We consider here bond angle here, bond length are mentioned here. In BF3 molecule bond angle is 120, but in case of BF2H 121. Bond angle is 120 in all the directions, but here it is variations. Bond length is also variation. The descriptor symmetrical implies that a species possesses a number of indistinguishable configurations. BF3 molecule is rotated in a plane of paper through 120 degree. Resulting structure is indistinguishable from the first. Another 120 rotation results the third distinguishable molecular orientation. This is not true if we carry out the same rotation operations on BF2H. The group theory is a mathematical treatment of symmetry. In this unit, we are going to familiar to the fundamental language of group theory. What are the fundamental language of group theory? The symmetry operator, symmetry element, point group, and character paper. These are all the language of group theory. The unit does not set out to give a comprehensive survey of molecular symmetry, but rather introduced some common terminology and its meaning. Now we are going to discuss with what are the symmetry operations and symmetry elements. If we apply that 120 degree rotation, just imagine that from year to year 120 degree, year to year 120 degree, year to year 120 degree. This color is indicates that fluorine atom that is in different color. Just you undergo 120 degree rotation. What happened? That rotation of trigonal planar BF3 molecule through 120 degree generates a representations of the structure that is indistinguishable from the first. Just it is changes the position, but there is no changes that bond angle and bond length. This is what symmetry operations. How we can define that symmetry operations? A symmetry operation is an operation performed on an object which leaves it in a configuration that is indistinguishable form and superimposable on the original configuration. That is the definition of what? Symmetric operation. Yeah, there are many types of symmetry operation are performed. For study of symmetry of the molecule means rotation about an n-fold axis, reflection through a plane of symmetry, reflection through a center of symmetry, and identity operator. These are all what here different symmetry operations. Now we are going to discuss with what is rotation about an n-fold axis. The symmetry operation of rotation about an n-fold axis is denoted by the symbol is Cn, in which the angle of rotation is 360 by n, where n is one integer. Applying these notations to the BF3 molecule gives what is the value of this? N is equal to 3. Means here, first rotation n is equal to 1, this n is equal to 2 and n is equal to 3. Here what is the angle here? 120. 360 by number of rotation 3. What we are getting angle of rotation is 120. In addition, BF3 also contains 3 two-fold C2 rotation axis, each coincident with a BF bond as shown in the figure. Just to see here, this is C2, C2, C2. This is C3 here, C3 and two-fold C2 axis symmetry possessed by the trigonal planar BF3 molecule. We consider in a molecule possess more than one type of n-axis. In such case, the axis of highest value of n is called the principal axis. It is the axis of higher molecular symmetry. For example, BF3 here C3 axis is the principal axis. Just we go through that here. The square planar molecules like XeF4. In that XeF4, one C2 axis coincides with the principal C4 axis. The molecule lies in sigma H, means plane of symmetry, which contains 2 C2 and 2 C2 axes. What is the reflection through a plane of symmetry? Means that mirror plane. The reflection of all parts of a molecule through a plane produces an indistinguishable configuration. Then the plane is called plane of symmetry. The symmetry operation performed is a reflection, and symmetry element is a mirror plane, and it is denoted by the symbol sigma. For BF3, the plane containing the molecular framework is a mirror plane. The plane lies perpendicular to the vertical principal axis. Then it is denoted by the symbol is what? Sigma H. Just we consider this water molecule. This possesses a C2 axis shown in the figure, but it contains two mirror planes, one containing the other, one perpendicular to it. Each plane contains the principal axis of rotation and so may be denoted as sigma B. This H2O molecule possesses one C2 axis and two mirror planes. The C2 axis and plane of symmetry that contains the H2O molecule. The secondly, the C2 axis and plane of symmetry that is perpendicular to the plane. This is the example of this reflection. Next, reflection to a center of symmetry means inversion center. If reflection of all parts of a molecule through the center of the molecule produces an indistinguishable configuration, The center of symmetry is called center of inversion. That is denoted by the symbol is I. Consider the molecules like CO2, trans N2, F2 and SF6 and benzene possess a center of symmetry. Next, inversion operation. So one of the simplest symmetry operation encountered is the inversion operation, whose element is a single point in space. The operation put a premium on the ability to recognize the origin of the coordinate system where all symmetry elements intersect. The several examples we have to taken for that inversion of operation. This inversion of operation. The molecules which contains an inversion center, dioxygen or sulfur, hexafluoride, octafluoroternate. First we consider here the inversion center of these tetrahedral molecules like that titanium tetrachloride. Here what happened here? To inversion, it changes its path. The titanium produces an orientation distinguishable from the original one. The chlorine atoms in the drawing have been subscribed to illustrate where the inversion operation move them. Consider example of the hexagonal bipyramidal structure of this FeCO5. Next concept, rotation about an axis followed by reflection through a plane perpendicular to this axis. These are all what improper rotation of this stannous involves rotation about 360 by n followed by reflection through a plane that is perpendicular to the rotation axis. The diagram illustrates the operation about one of the S4 axis in CH4. Identity operator. Identity operator is denoted by the symbol is capital E. This is the simplest operator and effectively identifies the molecular configuration. The operator E leaves the molecule unchanged. The successive operation, as we know, a particular symbol is used to denote a specific symmetry operation. For example, if we say that NH3 possesses a C3 axis, means that we can rotate the molecule through 120 degree, result a molecular configuration that is indistinguishable from the first. Actually, it is difficult to distinguish between the three hydrogen atoms, but for clarity they are labeled. Next we consider how the successive operations is going on that molecule here. Three rotation in ammonia are distinguishable using the notation C3, C32 and C33. The effect of the last operation is the same as that of the identity operator acting on NH3 in the initial configuration. Next we will consider that point group. Point group are the method of classifying the shapes of the molecule according to their symmetry element. The chemist classified molecule according to their symmetry. The collection of symmetry elements present in the molecule forms a group typically called the point group. The question arises here is why it is called a point group. We consider that each molecule has a set of symmetry operation that describes the molecule overall symmetry. The set of operations defines the point group. We consider that number and nature of symmetry elements of a given molecule are conveniently denoted by its and you rise to a label such as C2, C3b, T3d, OH or IH. These points belongs to the classes of C3 and group 4. Here, the point groups are hexahedral, tetrahedral, octahedral and icosahedral structure. Next we consider for this symmetry molecule in terms of one symmetry element provides information about this property. For example, each BF3 and ammonia possess threefold axis of symmetry, but their structures and overall symmetries are different. BF3 is trigonal planar and NH3 is trigonal pyramidal. On the other hand, descriptions and symmetry of these molecules in terms of their respective point groups provides information about the all symmetry elements. These are all characteristic symmetry elements of some important class of point groups. The characteristic symmetry elements of the tetrahedral, octahedral and icosahedral are omitted because the point groups are really identified. No distinction is made in this table between sigma V and sigma D plane of symmetry. Next we consider C infinity to V point group. Example of this here criteria are met by asymmetrical atoms like HF, CO and CN, and linear polyatomic molecules that do not possess a center of symmetry. This is a linear molecular space, can be distinguished, can be classified according to whether they possess a center of symmetry or not. All linear spaces possess a sigma infinity axis rotation and infinite number of sigma v plane. In that D2H, D infinity H point group, the symmetric diatomic molecules like oxygen, hydrogen and linear polymolecules that has a center of symmetry. Generally, these molecules which possess a sigma plane in addition to C infinity axis and infinite number of Next we consider this tetrahedral structure, this octahedral, this these are all octahedral symmetry molecules. Next, determining the point group of a molecule or molecular ion. How to determine that? The applications of systematic approach is essential for the assignment of a point group. Otherwise, the symmetry elements will be missed. We consider a structure of this titanium oxide. There is a principal CN axis and that molecular linear mirror plane, center of inversions, center of symmetry, etc. Now, how to determine the point group of trans N2F2 molecule? That trans F2F2 molecules here, the molecule is linear. No. Does trans NF2 have octahedral, tetrahedral or icosahedral symmetry? No. CN axis, yes. And this all stops to determine the molecule. Determinations of the point group like BF3 molecule. Determination of POCl3 molecule. Just we consider some other information regarding to that. Here first we have to calculate how many bonds are there, linears are there. Similarly, where it is, we are going to try that molecular. These three molecules are very important. N2, F2. There is a CN axis, yes. C2 axis perpendicular to the plane of the paper and passing through the midpoint. Or there 2C2 axis perpendicular to the principal axis? No. There is a sigma h means perpendicular to the principal axis. That is what? Yes. This is the way to determine the molecular structures by using these molecules. Like here POCl3 molecule. In POCl3 molecule it is a linear. No. Does POCl2 have tetrahedral, octahedral and icosahedral symmetry? No. There is a CN axis, yes, because C3 axis running along the oxygen phosphorus bond. There are 3 C2 axes perpendicular to the principal axis. There is a sigma H plane that is perpendicular to the principal axis. There are sigma NV planes containing the principal axis. Now I am going to summarize this unit. from these topics, group theory or symmetry of molecules is important packaging, important for understanding the structures of properties of compounds. In chemistry, many phenomena can be classified, explained on considerations of symmetry. And the symmetry operation is, or generally symmetrical operation applied to molecules. The application of the symmetry operations to a particular molecular geometry produces a symmetry operation which is redistinguishable. The few basic theories, operations that need to be considered are identity, rotation, reflection, introversion, and rotation, reflection. The symmetric properties of molecules are described as the set of valid symmetry operation. Next, all these special points along the symmetry elements, the symmetry plane, axis, center of inversions do not change their positions during the corresponding symmetry operations. We consider the terms of this identity operation, inversion and reflection, and all n-fold rotations all are discussed in that unit. In the point of examination, we studied that some important molecules like benzene, borosine, pyridine, and sulfur-based molecules like four-fold principal rotation. Draw the structures. Draw the structure of B5H7 and some important definitions of this molecule. Thank you.